Okay, I'm gonna explain CodeForces round A-A1, div 3. So, I think the questions in this was pretty interesting. It was pretty like algorithmic, and yeah. Okay, first question here. Okay, you have an array of n integers and you have to paint elements. The cost is the max of the color minus the min of the color. The cost is the sum of all colors, and you can paint as many colors as you want. So you can see that the only thing that changes the cost of one color is its max and its min. So there's no point painting like more than two of one color. So you want to have like the biggest max and smallest min, and you never want like max minus min uh to be negative. So, and you have to paint each element. So you basically just sort the array, and then uh, you just minus the bigger ones from the smaller ones. Yeah. While it's L is smaller than R. Yeah, I don't know why. Yeah. Okay. You have to paint each element, so this is not really right, but it still worked. Okay. Second question, long. Basically, this question you can flip negatives to positives. The max and the minimum, you have to find the minimum number of operations. So this is basically just seeing how many continuous subsegments there are, and you can just keep track of that. Just basic keeping track. If it's smaller than 0, you can and if it's not continuous, you have to add 1, but if it's still continuous, you don't. And if it's 0, you can keep it continuous. Yeah. Okay, for C, this question was pretty easy. So you basically need to find the sum, that the path from 1 to the vertex n takes. You see how big n is? Yeah, so the path from the vertex to n, it's basically just going I guess like from n to 1. You can think of it that way. You just basically go up layers. And to go up layers, you just divide by 2. Yeah, so you just divide by 2, and then each time you just add it. Yeah. Okay, apple tree. So this question was about finding how many combinations, the number of pairs of vertices that apples can fall from the tree. So for each A and B, you need to know the number of its children that are leaf nodes. And once you know that, you can multiply the number of children this leaf node has to the number of children this leaf node has. Like, I delete this. Yeah, so if this leaf node has like 1, 2, 3, 4, this has like 4, 5, 6, 7. So this one could be any of these, so that's 4. This one could be any of these times 4. And it doesn't matter if these are duplicates and whatever. It's still just the number of leaf nodes that are in the children of this one times that one. Yeah. So you just basically keep track of that using kind of like a DP method, yeah. Yeah. You just child u plus child v, just add from its children how many leaves, this is how many leaves it has, and then if it's a leaf itself, then leaf is 1. Yeah, just multiply it. Okay, here, tracking segments. So here in this question, you have a bunch of segments that if any one of the segments has more ones than zeros, then if any of the segments have more ones than zeros, then the array is beautiful. Then it's good. It's done. So you basically want to know when it's good, when it's done. And if you take like the most brute force approach, that would mean you just simulate when you make each 0 a 1, and you simulate it. So that's n, and then for every time you make a 0 a 1, you have to go through all of the m segments to see if any one of them has turned beautiful. As a result, that's a n times m, without even considering the time it takes to query the segments. So an idea here is you guess when the when the array turns beautiful. So you just do binary search on that, and that'll be log2 q, the number of changes, times then after you do that, you just use segment tree to find if each segment is beautiful in like log time. Yeah, it's basic segment tree, and then you build the segment tree and you query all m segments, and then you just binary search guess when the array turns beautiful. Yeah. Okay. And this question F1, I didn't solve this during the contest, but yeah, I solved it after. So basically this question is about building a tree. So you're basically building a tree, and then each new node you add can either have a weight of 1 or -1. And what this means is, like, the observation that is like most important here is that if you have a node u, or let's put this as the root node right now, and the root node has a weight of 1, but you can also not take it and have a weight of 0. So you have this root node, and the elements it can take is, or the subsegment sums could be 0 or 1, and you connect a node v. So this node can either be positive or negative. So this means it can expand this range only by 1, or because it's only positive 1 or -1, it can only expand this range by 1. So it can only expand its parents L plus 1, or it can do this L or like -1, I mean, plus 1. So this means the subsegment sums, or the possible subsegment sums, are continuous, since each time you can only plus 1 or -1 from the L or R. So since we now know that the range of values that the subsegment of a node can have, or the path on this path can have, is continuous, that means we only need to keep track of the biggest and the smallest values. Okay, so that determines the range, the biggest and the smallest, like the L and the R. Yeah. So basically here you have the here I have Pmax and Pmin. This is if you're taking the current node, and B max and B min is the best, or like the minimum and the max of the previous or the current. Not include, or it could include the present, but it doesn't need to. Okay, so the P max comes from the present, comes from the max of the present plus the current value, or you just take the current value. And the best is either the best of the parent or taking the current, because the only thing that changes from U to V is either is if you take the current node or the V node, and that is that comes from also taking like the best from the previous, including when you take the previous node, since it has to make a continuous subsegment.